So we have developed some formalism, some things that give us equations that would tell us how a system will evolve as a function of time. We know that the time evolution operator is particularly simple when the Hamiltonian is time independent. In our discussions amongst ourselves, we've looked at some examples of time evolving wave packets. And now what we're going to do is take a little bit of a look at how we can formulate the time evolution problem, so the quantum dynamics, for, let's say, an arbitrary Hamiltonian. This will get us starting to think about how to deal with this. The way I'm going to show it now is where we're going to treat the system exactly, right? So to treat a system in quantum mechanics exactly, you need to represent it in a basis and write down a Hamiltonian matrix that's finite, obviously, because we don't have an infinite size memory for a computer, which is going to introduce some numerical accuracy issues, but theoretically it's exact if you had an infinitely large matrix. All right? And what's nice about this way is that it converts, or essentially allows us to use, any kind of linear ordinary differential equation solver that you might have. And in MATLAB, for example, it's one line. I'm sure in other programming environments it also can be one line, to evolve the system, the state of the system, from one time to another. All you need to know is how to evaluate the Hamiltonian at any point in time. Multiply it by a vector and you'll see that that gets you the derivative. So let me show you how to do this. All right, just to remind ourselves, of course we know what the Schrödinger equation is. Minus I over h bar times h psi of t. Okay? This is an equation in Hilbert space. It's not exactly immediately obvious maybe how you put this into a numerical representation. Okay, so what we're going to do is we're simply going to choose a basis. All right, now what basis should we choose? You might choose a basis that, for example, if the Hamiltonian is a relatively simple Hamiltonian that you know, and there's something that depends on time that's different. Later on, we'll see how you can do perturbation theory, but we're not talking about perturbation theory now. We're just saying as long as you can break this into two pieces, a piece that's time independent and time that's time dependent, and this piece, the energy scale associated with this thing is not so big compared to that one, it would be very sensible to try to figure out what the eigenvectors of this Hamiltonian were to express your problem. But that's not required. You can use any basis that satisfies the same boundary conditions that your problem has. Right? But some will be better than others. All right, so I'm going to assume that we have some basis. Now, it doesn't have to be the basis of this Hamiltonian, so we're going to just say it's an arbitrary orthonormal basis. So you might denote that somehow like this. When I was in grad school, I got into this notation. I don't know if it's really useful or not, but it's a set of vectors, and then they're perpendicular, and then I think I had some professor who drew the unit operator in this sort of double one way. So I just sort of adopted this. Whatever you want to call it. It's orthogonal. What that means is orthonormal. It means that chi n, chi m, or if you want to use, in my notes, what am I using? I think I just use subscripts. This is equal to delta nm. Right? A pretty obvious choice for a basis. You don't have to have it that way, as we discussed with the Cartesian coordinates. They don't have to be perpendicular to each other. It's just a lot more simple to do it when they are. What do we know? We know that we can write the identity operator. So 1 is equal to the sum on k, chi k, chi k. Right? That's our spectral resolution of the identity. It doesn't matter if these aren't eigenvectors of the Hamiltonian. You still can use that language. So we can multiply our state vector by this, surely. 1 times psi of t is absolutely equal to psi of k. So chi k, I meant. Chi k, psi of t. All right. So what this tells us is this scalar product here is a coefficient, right? This is a number. Certainly it'll evolve as a function of time. Phase will happen. but we can nevertheless, I call it something. Let's call it ck of t. It's the amount that the state vector projects along the chi k direction at time t. All right, so that means we can now put this into the Schrödinger equation. So we put in d by dt, plug this expansion. Now this is a number, I can move it however I like. So I put it on the left-hand side. And what is this equal to? Well, we know what the right-hand side is. Minus I over h bar, h of t, and then it's the whole expansion again. Right, and if this is getting nervous, just go back to a problem you understand. Let's pretend we're trying to do a harmonic oscillator and we put on a field, so there'll be something changing as a function of time on the Hamiltonian, but the h naught part is just a normal harmonic oscillator Hamiltonian. This would be one of the harmonic oscillator eigenfunctions, and we need to just figure out whatever our state vector is going to be, it's going to be that projection. Now when we actually solve it, we're going to be solving for these coefficients, so we would be going back to the harmonic oscillators if we wanted to plot the function as a function of space. But this is the basic idea. All right, so what we want to do is we're going, as you normally do when you have these kind of sums, it's conventional, or that the standard way of making progress is to operate or to multiply on the left by potentially another of the basis vectors. So we're going to multiply on the left by chi j, all right? Chi j on the left. And so what happens when we do this? It's going to be chi j on the whole thing, left and right-hand side of the equation. All right? This comes in and tetrises up to here, right? Because this is a number, that's a derivative, it goes in. So when we do that, we get sum of k. All right? And we can even bring the derivative in, but we can leave it out, it doesn't matter. Well, I'm going to bring it in. ck of t, and what do we see here? Chi j, chi k. We know what that is because we already said that we chose our basis wisely. This is a delta function, jk. That means out of all the sum of all the terms, only one of them survives, the one when k is equal to j. All right, on the right-hand side, what do we have? All right, now we bring this across, and it can tetris until it hits an operator or another vector. So in this case, it hits the Hamiltonian. All right, and so we have minus I over h bar, chi j, h of t, all right. Now, there's no reason that this has to stay outside of the sum. We can bring this in. It doesn't depend on k. So we can bring this all the way across. This can go and tetris all the way over to there as well. Let me bring it in this way. Well, this sigmas look horrible. There you go. So there's k. We have chi j, h, chi k, and then we'll have c of t over here. ck of t over here. Okay, so when we look at this, what we see is that we have cj on the left. So it turns out the notation looks more convenient if we do it this way. So it's the time derivative of cj of t. Everything else goes away, the sum goes away, is equal to minus I over h bar, sum on k. And what is this? This is a matrix element, right? So just like we had before, it's the h, j, k element of the Hamiltonian multiplied by ck. All right. And so if you have remembered from your linear algebra, this is nothing other than the formula for a matrix times a vector. All right, so we automatically get out this but it's only the jth term, right? So it's not the whole vector, it's the jth term. All right, so when we realize we can do this for every single term j, then we'll have done it for the total multiplication of this matrix times the vector. So we can summarize everything here like this. You can write d by dt, okay, of the c coefficients, which I will write in this way. c1 of t, c2 of t, all the way down to however many we have. Now, in practice, of course, we need to have a finite number. In theory, we could have as many as we want. Is equal to minus I over h bar times the matrix. So that'll be h11 of t, h22, h12, h21, oops, 21, and so on in all these dimensions. And then I ran out of space, unfortunately. Sorry about that. And then over here we have the C1, C2 again. Okay? So sometimes people will write this, depends on sort of the generation of people. In the old days, before you had Microsoft Word or whatever to do your papers, you would type out your equations and then put in the the changes to the characters by hand. And so the one way you would note a bold is you would undersquiggle it like this, which now we interpret as like it's spelled wrong, right? So this would be a vector note, a notation for a vector, a capital, a number that's bold but not italics. Even now we call that a vector. With a dot on it just means a time derivative. I over h bar minus I over h bar, of course. And then we have h, and they've decided that double undersquiggle is a matrix. These are all functions of time, so maybe I should put that in explicitly, times the vector c. All right, so that is the Schrödinger equation written as a system of linear equations, right? A system of linear differential equations. And what's so great about this is that now you can compute these expansion coefficients, which you can get back then to the state vector, as long as you remember what basis you wrote your stuff in, this basis. You can get the wave function or the state vector at any point in time. All you have to do is multiply the Hamiltonian at time t times the coefficients at time t. Now that you have to supply initial conditions, as you usually do for ordinary differential equations. But that matrix multiplication is all you have to do because it's literally it's equal to the derivative, right? And then there are all kinds of clever schemes for numerically solving this ordinary differential equation. You know, popular ones are things like the Runge-Kutta method, and they have different, error properties and whether or not this solution is highly oscillatory. Those are all sort of these interesting numerical things to consider. But in MATLAB, it's one line. You tell it the function that computes the derivative. You give it the state vector or the vector at that time, and then it will propagate the equation for you. Of course, it also monitors the error for the possible. These are not numerically exact methods, but the errors can be very small, especially if it takes small step sizes. Most modern solvers can also take adaptive step sizes, so they take very fine steps when the solution varies rapidly and take bigger steps when it goes slower. All right, so this allows us, in principle then, to solve any problem in quantum mechanics, provided, and this is the big problem, right? Provided we can write the Hamiltonian like this. Now, what's the problem that you end up with? So as you discovered in our particle in the box with a ramp problem, you actually need quite a lot of states to approximate or to faithfully reproduce the function, the eigenfunctions of the Hamiltonian, as the perturbation from the difference from your reference system changes more and more. Now, that's only for one dimension. For every dimension we add, we're going to have that many states associated with it. So let's say it was 10. You need 10 basis vectors per degree of freedom. Okay? So I have 10 basis vectors per degree of freedom, and I have one particle. It might only have 3 dimensions. That's not so bad, but it's still, I need 10 for each of the 3 degrees of freedom of a particle. So that's 10 times 10 times 10, 10 cubed. All right, that's not so bad. But now if I have 2 particles, I have this squared. Yes, and now you see the problem. The more degrees of freedom you have, whether it's particles or dimensions, it could be vibrations, it could be electronic states, whatever it is, the more dimensions you include into your problem, the bigger does your basis grow in a completely exponential way. And that's why quantum mechanics has this horrible scaling. So unless you can deduce or distill your problem down to a small, important set of degrees of freedom, and of course people always try to do that, then these are doable, but they're not tractable. That's unfortunate. But a lot of times you don't really care about that. You have like maybe many degrees of freedom, you boil it down to a reaction coordinate, then you can propagate, no problem, any wave function on a few degrees of freedom by putting it into a basis. Right? And so that is something that people have been doing for decades. There's nothing particularly new about this. What's nice about it now, you fire up your laptop, you can code this whole thing in an hour if you just know how to write the Hamiltonian down. Right? And it's even better if the only thing that's changing in the matrix elements are something like an electric field. Because then you can include an electric field like, a cosine varying function, or even a laser pulse, a pulse that goes on and turns off. You can add a pulse with chirp. All right, and we're going to do all of those things as examples as for the problem sets, because it's actually quite a lot of fun to be able to see the quantum evolution. Here we're looking at the evolution of the state vector through these coefficients. We could also look at the density operator. But once you have these coefficients, you can calculate any observable property, position, momentum, angular momentum, whatever it is that you have. A lot of times people will be interested in knowing the populations of the states. That's very important for chemical relaxation, energy transfer, models of chemical reactions that are photo-triggered, for example, if it's a spectroscopy course. Or if you're interested in the light absorption and emission, you'll want to know about the expectation value of the dipole moment operator, which we can also calculate. And then that allows us to calculate things like the absorption spectrum, or the emission, or the pump probe. We can even do nonlinear optics with this. Right? So we will be able to do all of those things simply because we can always time evolve the Hamiltonian, the Schrödinger equation, if we have a way of calculating the Hamiltonian. It's really that simple. If you can't do this though, then you're kind of out of luck.